Today we're going to talk about how to find the volume obtained by rotating the region bounded by these three curves about the line x equals 2. So we've been given the curves y equals x cubed, y equals 0, and x equals 1. Between the three of these, they bound a particular region, and we're supposed to rotate that region around the line x equals 2 and find the volume that we obtain when we perform that rotation. So the first thing we need to do is realize that we're rotating around a line or around an axis of rotation x equals 2, and that's the vertical line x equals 2. So whenever we're rotating around a line x equals something, it's probably best to solve the equations that we're given here for x in terms of y. So right now we have y equals x cubed and y equals 0. We want to solve those for something in terms of x if we can. So for example, y equals x cubed, if we take the third root of both sides, in other words, if we raise both sides to the 1/3 power, then what we'll get is x equals y to the 1/3. And now this equation is solved for x in terms of y. We also have the line y equals 0, which we can't really solve for x, and we have the line x equals 1. So we're in good shape now. What we should do next is graph a picture of these as best as we can so that we have an idea of what we're dealing with. So if we draw here an xy coordinate system, the first thing that we need to do is graph our equation. So we have x equals y cubed. That's the same thing as y equals x cubed, and we know that the graph of y equals x cubed looks something like this. So if we graph it like this, it looks something like this, and then it would come down here and go off in that direction, but it's basically this shape here. So we have y equals x cubed, so we'll actually call this y to the 1/3. And then we have y equals 0. So that line, y equals 0, is just going to be here, y equals 0, and we'll say y equals 0 there. And then we have x equals 1, so the line x equals 1, and we'll say that that's roughly here, the line x equals 1. So now we've defined an area. We have this area here between the three curves, and we're going to rotate this region around the line x equals 2. So if we have the line here, x equals 2, we call that the axis of rotation. So what we're going to do is we're going to take this region here in purple, and we're going to rotate it around this line. So if we rotated it, eventually, we'd have the region over here, like this on this side, and we're going to rotate around the whole thing, and it's going to form a volume, and we want to find the value of that volume. So what we need to do is realize that we have intersection points, right? So our curves intersect each other here, and they intersect each other here. We know that the value here is 0, 0 at the origin. This intersection point is at 1, 1. If we didn't know that, we could set our curves equal to one another. We could set y to the 1/3 equal to 1 because they're both equal to x, and we would see y to the 1/3 is equal to 1. We could cube both sides and we'd get y equals 1, and so we know that the value there is 1. Those are our limits of integration. Those are going to be our values for a and b. So a will be 0 and b will be 1 because our limits of integration, we're going to be integrating on this range here for y from 0 to 1. So let's start looking at our formula here because we already know a is going to be 0 and b is going to be 1. What our formula here for the volume tells us is that we have AOR here, which I've just abbreviated. It's basically axis of rotation. So we know that the axis of rotation is the line x equals 2. So we're just going to be plugging in 2 for axis of rotation. But then we have outer curve and inner curve. So the outer curve is the curve that's farther away from the axis of rotation. And in this case, that's the curve y to the 1/3 because we basically have this distance here between the axis of rotation and the outer curve. Then we have the inner curve, which is the vertical line x equals 1. So that distance is right here, between the axis of rotation and the inner curve, the curve that's closer to the axis of rotation. The difference between them, this distance right here, is going to be, at any given point, the area of this shape. So that's why when we subtract the inner curve from the outer curve, we get the area. And if we integrate that and we multiply by pi, then we're going to get the volume of rotation. So once you know the outer curve, the curve that's farther away from the axis of rotation, and the inner curve, the curve that's closer to the axis of rotation, plugging into your formula is simple. So we have here the integral from 0 to 1, because the point where the curves intersect each other at the lower bound is 0 and the upper bound is 1. So we have 0 to 1 of pi times axis of rotation 2 minus the outer curve. And the equation of the outer curve is y to the 1/3. So y to the 1/3 power squared minus pi times axis of rotation minus the inner curve, which we know is x equals 1. So we just get 1 there, squared, and then dy. And whenever you're rotating around a vertical line, x equals 2, so whenever you're rotating around x equals something, you know that you want to plug in values for your outer and inner curve that are in terms of y. So we have y here, and we have the line x equals 1. We know we're going to have dy, and we know that our limits of integration are going to be y values from 0 to 1, as opposed to when you're rotating around a line y equals something and it's a horizontal line, you know that you're going to have x values here. You're going to have, for example, x to the 1/3 and 1 here. You're going to have dx, and your limits of integration are going to be, like 0 and 1 here, x values along the x-axis. But we have the opposite case here where we're rotating about a vertical line, so we have y values and y limits of integration. So now it's just a matter of simplifying the integral as much as we can and evaluating the limits of integration. So we have, first of all, we can always factor out pi because we have pi as a constant coefficient on both of our terms. So we'll factor out pi and we'll say 0 to 1 of 2 minus y to the 1/3 squared minus 2 minus 1 is just 1. When we square that, we just get 1, and then dy. So now let's go ahead and multiply out this 2 minus y to the 1/3 squared, so we'll FOIL it. When we multiply 2 minus y to the 1/3 times 2 minus y to the 1/3, we get 4 minus 4y to the 1/3 power plus y to the 2/3 minus 1 dy. And now we can go ahead and take the integral. So we'll get pi times 4y minus 4y to the 1/3. We add 1 to the exponent and we get 4/3. We divide 4 by 4/3, which is the same as multiplying it by 3/4. So we get 3y to the 4/3. Then we have y to the 2/3. We add 1 to the exponent and we get 5/3. We divide by 5/3, so we get plus 3/5 y to the 5/3. And then minus 1 just becomes minus y, and we're going to be evaluating that on the limits of integration 0 to 1. Now, as you know, when we're evaluating on limits of integration, we plug in the top number first, so we'll plug in 1, and then subtract from that whatever we get when we plug in 0. So we get pi times, and we'll plug in 1. 4 times 1 is just 1. 1 to the 4/3 is still just 1 times 3 is 3, so we get minus 3. 1 to the 5/3 is still 1 times 3/5 is just 3/5, and then minus 1. Now we could subtract what we get when we plug in 0, but we'll just get 0, 0, 0, and 0, so no sense in writing all of those out, and this is all we're left with. We want to go ahead and find a least common denominator, which is going to be 5. So in order to get a least common denominator of 5, we'll multiply each of these other terms by 5 over 5, and we'll get 20 over 5 minus 15 over 5 plus 3/5 minus 5/5. And when we take 20 minus 15 plus 3 minus 5, we get a volume of 3 pi over 5. And that is the value of the volume obtained by rotating this region here about the line x equals 2. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.